I'm going to start out today sort of backing up what Ben just mentioned about the chance that cooking is going to release contaminants into your home. And first of all, I want to talk about when things get hot, what happens. Those particles that Ben just talked about that are one of our primary contaminants of concern for healthy indoor air are often generated when things get hot. And if you're burning gas or you have a hot electric element, they get hot enough to make a lot of particles, particularly ultrafine particles. But also other things get produced too. When you burn natural gas, there is carbon dioxide and lots of water vapor. Also oxides of nitrogen and formaldehyde and other contaminants of concern. So that's just from the fact that you've made things hot when you're cooking. Then there's the food itself, where there's a whole range of volatile organic compounds that are released and particles. And when we're talking about cooking pollutants, we're talking about all of these. And it really doesn't matter what you're cooking, you're going to mix some contaminants, but as you can imagine, different cooking emits different contaminants. Similarly, when you're making things hot, whether you burn natural gas or have an electric induction element or just an electric resistance element, there are different quantities of contaminants produced. And I'm going to give one quick example here, which is simply related to how we make things hot when we cook. And this is looking at the emission of ultrafine particles. And here we're comparing gas cooktops to induction cooktops to resistance cooktops. And you can see induction cooktops emit a lot less of these ultrafine particles simply because they don't get as hot as cooking with gas or cooking with an electric resistance element. Another thing to note is that when we're talking about cooker hoods or range hoods, this is something with a fan in it that is designed to suck the air from above the cooktop and do something with it. If this fan simply blows the air back in your face, we're not going to count that as a cooker hood. It didn't get rid of the contaminants. These things must vent to outside. And in the example photograph there, a quick way to check is if you have one of these things mounted to some cupboards, if you open them up and there's no vent in there, and when you turn it on, you feel air blowing in your face, then we're not going to count that as a cooker hood from the perspective of controlling the concentration of those contaminants. Similarly, something we call a downdraft kitchen ventilator, this often is something that pops up out of the countertop or from the back of a cooktop. There's no hood over the cooking area, and we're not going to call that a cooker hood from the point of view of our discussions today. So how can we determine how effective your cooker hood is? And this idea of something called capture efficiency is what I'm going to talk about for the next 10 minutes or so. What capture efficiency tells you is what fraction of all those contaminants that got emitted from the cooktop get sucked into the fan and blown outside your kitchen so they're not contaminating the kitchen or the rest of your home. And we have a definition of capture efficiency. And when we do our testing for capture efficiency, whether it's in-home testing or in the laboratory, we will often seed the plume of contaminants with carbon dioxide, mostly because it's a readily available gas. It's quite easy to measure its concentrations with relatively inexpensive equipment. And if you have a gas burner, we can measure the CO2 generation rate based on the gas consumption. Or for laboratory testing, we'll often deliberately inject CO2 at a known rate. If we measure the concentration of carbon dioxide in several locations, in this case, in the outside air coming in to the space, in the room itself, and in the exhaust duct from the fan, this is the air that's exhausted from over the top of the cooktop, we can use this simple relationship to determine what fraction of what got emitted from the cooktop is captured and removed from the room. And we call this capture efficiency. We've done various studies, not just LBL, but several other research organizations have also done similar work, where we look at performance both under very controlled laboratory conditions, where we know very precisely what cooking is happening, how long it's happening for, and we know all the flow rates and so on. And we've also done testing in homes, which is always a little bit trickier because we can't control everything like we can in the lab. And we have to come up with strange ways to measure airflow. If you look at the figure in the far right there, you can see we've got a little fan flow meter device with some flexible ducting to try and measure the exhaust flow out of that cooker hood. So things are often a little bit easier from an engineering perspective when we want to measure stuff in the lab, but we have come up with techniques to measure emission rates in homes. And what happens when we do this? So this is a plot looking at, I think it's 15 or 16 different cooker hoods, and each one in a different home. And we measure the capture efficiency from emissions from back and front burners separately. Because a big question in our work has been, would there be a difference? We might expect there to be. Then combined as turning all the burners on. And in some of these cases, we looked at what happened when you turned on the oven. And as you can see, for each house, there is quite a big range of capture efficiency depending on where the contaminants are coming from, back burners, front burners, or the oven. And in the interest of openness, I have to point out that one of these is the cooker hood in my kitchen. And I'm glad to see it was one of the better ones, but you could say I had insider information when I was selecting mine. But the key thing I want you to note from this is that there's an enormous range from effectively zero capture efficiency in some cases to 100% capture efficiency in others. And if you go and buy a cooker hood, you have no way of knowing where you are on the spectrum. What if we go to the lab and do some more controlled testing? So this is results from 7 different cooker hoods that were tested in a laboratory, and the legend there, the different colored symbols refer to the different hoods. And we tested the capture efficiency at different airflows. You can see the horizontal axis in each case is the airflow through the hood. And you can see that generally, as you might expect, if more air is sucked out of the cooker hood and goes to outside, you get better capture efficiency. But you can also see from this that the front and the back capture efficiency is different. So we almost always have better capture efficiency on back burners than front burners. And we also see that we can get the same capture efficiency over a big flow range depending on the hood that we're using. Similarly, if we look at results for the same airflow, we get a big range of capture efficiency. So this big range in performance means that currently our way of specifying do you have a reasonable hood probably isn't good enough. For example, the standard that I chair, which is ASHRAE 622, specifies a fixed airflow as a minimum airflow for kitchen ventilation. And we can see from these results, if you just pick a minimum airflow, the range in performance is really quite large. And maybe that metric of picking an individual airflow isn't quite good enough. And so when we look at all these results, it's clear that we need some sort of rating method to figure out what capture efficiency is for these hoods. And this is just a quick note so that you can get an idea of where on the spectrum of performance your own kitchen might be. A lot of that variability that we see has to do with how well the hood covers the cooking elements. So this is looking down onto a cooktop. You can see the small microwave oven has very bad coverage. This device had very poor capture efficiency. This device covers a bit more, particularly it covers the back burners, and the results for this system were that we got good capture efficiency on the back burners, not so good on the front. But if you stand on a chair and look down and you see this, where all the burners are covered, you get much, much better capture efficiency. So there's a lot of that variability I showed in those laboratory and field tests is due to this geometry factor. So how can we do standardized testing? We're basically going to have to find a fixed way that all these devices could be compared so we could rate them. So we came up with a basic way of testing in a laboratory. So this is a kitchen-sized and shaped space that has an electric cooktop in this case, but we have also done experiments with gas where we deliberately designed a quote-unquote kitchen that would always be the same. So those cabinets that you see there will always be in the same locations. They will always be the same size. The cooktop will always be at the same height. And we will always sample our tracer gas and temperature and humidity and other experimental values in exactly the same locations. We did a lot of experiments to find out where those locations should be to be best representative of the space. We also needed a standardized way to emit our tracer gas, and this is because different cooktops have got different burners of different shapes for gas cooking and different shapes and sized electric elements. And we found that the size and shape and power outputs of the various heating elements would change the capture efficiency. So we needed to standardize that. And we came up with this idea of designing an emitter plate, which is a way of systematically introducing the tracer gas in a very uniform way. These are devices that can be machined in a machine shop, and if everybody uses the same one, we'll all be emitting the same way, which is what in standardized testing. We also did experiments to look at what sort of temperatures and power inputs were used in typical cooking events, and we looked at the research literature to see what would have been written about this. And we came up with a typical cooking event would have temperatures of about 160 degrees C and 600 watts per burner. Clearly, this varies a lot depending on the cooking that you're doing, but this is not the hottest and not the most power that you would use. It's similarly not the coldest and not the least power that you might use. One key thing here is we only test on using the front burners in this standardized testing because we found out that was the most challenging aspect of this. The back burner capture efficiency, like I said previously, is basically almost always much better than the front burner. So if you want to challenge these devices, we use the front burners. So here are some preliminary test results from 8 different cooker hoods tested using this procedure. You can see that we get a range of capture efficiency with flow, just like with our previous testing. The important thing is we repeated these tests over and over and over again to see, do we always get the same result? And in terms of percentage capture efficiency, the answer is yes, because we are controlling the temperature and the power, the size of the emitters and all of those various factors, and we have it in a fixed room with fixed cabinets, we get the capture efficiency within about plus or minus 0.5% capture efficiency over all these tests that you see here. And the very worst situation was about plus or minus 1.4%. And we felt that that was it would be very hard to do better than that in terms of a repeatable test. So that seemed to be reasonable. That test procedure I just talked about has been turned into an ASTM test method. It's E3087. And it's about to be used in the US anyway, by the Home Ventilating Institute, who do certification and rating of ventilation products. And currently they rate for things like airflow, power consumption, noise levels, and so on. And they're going to add an extra column, if you will, in their rating that says what the capture efficiency is for kitchen ventilation systems. So that's where we are with standardized testing. I just want to talk briefly now about the fact that standardized testing is really only for hoods that mount up against a wall, as you could see in the photographs and the examples I gave. We also want to think about island cooktops and exhausting from them, and also downdraft systems. So we've developed a second larger test chamber. We needed the larger test chamber mostly because when you're putting an island in, which is basically a cooktop in the middle of the room, you need room all around it, and the smaller test chamber really wasn't suitable for that. And this is what it looks like. Again, we're using the same emitters. We have standardized kitchen cabinets in fixed locations, fixed dimensions. We're injecting tracer gases just like we were in the other test chambers. So the test procedure is basically the same. What's changed is the geometry of the situation here. We're in a different room. We're not up against the wall. We have this island cooktop in the middle of it. And here's some preliminary results from the island cooktop testing. Again, we see that if we look at different airflow rates, again, we get better capture at the higher airflow rates. Those are the different shape symbols that you see in the plots here. We also found that the impact of the input power to cooktop burners was a bit more significant than for the wall-mounted devices. And here we're just showing some of the variability in input power and the emitter surface temperature and how it changes that capture efficiency. And although we haven't formally decided it, we're probably going to end up testing very close to the burner power that we used for the wall-mount devices at about 600 watts, because after about 400 watts, the results become much more consistent. But there's interesting things happening at lower powers where we see that, for example, at 0, if we don't have any heat at all and we just turn on the fan, the capture efficiency is actually effectively at its lowest point. With a little bit of heat, we get the best capture, and then it goes down again. So there's interesting physics involved here, which I'm not going to get into today. But we need to do these sort of experiments that when we pick a standardized test, that we're in a range or a regime where the results are going to be consistent. So I just want to sum up here about what to look for in good kitchen venting based on these field tests and laboratory tests. There's this simple geometry issue of, does the cooker hood actually cover the burners? We've developed a standardized way of capture efficiency rating, and these will likely be coming soon to standards, and devices will be labeled. For example, we might say in a standard that you have to have better than 80% capture efficiency, and that might replace the current requirements that we have for minimum airflows. In terms of getting good capture efficiency with current devices, it really gets good above a flow of about 100 liters a second or 200 cubic feet per minute. Look for devices that are quiet, simply because we've done a lot of other survey studies where people use the hoods a lot more if they are quiet. If you're installing these things, use the shortest path to outside for your ducting. The more ducting you add, the lower flow you'll get and the noisier it gets, and that both impacts the performance. Something I didn't mention earlier was, of course, capture efficiency changes depending on mounting height, and what we found is that if you follow the manufacturer's instructions, they will often give a relatively narrow range for mounting height. We found that if you stick to that, the capture efficiency doesn't change too much. The capture efficiency changes more if you get much higher than what manufacturers generally recommend for installation heights. So the guidance the manufacturers are giving is good. And lastly, if you're remodeling your kitchen or you're buying a new cooking device, an induction cooktop does have less emissions in terms of particles and so on compared with gas and electric resistance. And last little bit about, if you're going to be cooking your evening meal later today or maybe tomorrow or whenever you're cooking, if you use back burners, you'll always get better capture efficiency and less contaminants in your home. And even if you find that your hood is very noisy on high speed, use it on low speed. Your capture efficiency might not be great, but it's way better than doing nothing. And with that, I will stop talking and see if there are any questions.